In this second video, we're going to talk about how to solve force problems when you have diagonal forces and the diagonal force that you have is actually an unknown value. So far we've only seen it when you actually know the diagonal. Now it's really the same process, but there is a bit of a trick to it that I would like to show you. Again, as with all other problems, don't forget to use your 6 steps to solving all force problems. All right, so let's identify our variables. We know the mass is 2.4 kilograms. We know the angle is 13 degrees. We know it's not accelerating in both the y and the x direction. And I'm looking for how much force is the boy pushing with horizontally. So if we draw a free body diagram, we should get something that looks something like this, where we have a weight downwards, or also known as force of gravity. The boy is pushing horizontally, as described earlier, and then the rope, because it's at an angle of 13 degrees to be specific, with respect to the vertical, the tension's off at an angle as well. We could do the same thing with the vertical direction, and we're going to pretty much find the exact same thing, that t cosine theta is equal to the weight, because there's no net force vertically either. Now that we've got our two equations, we want to say, hey, look, which equation do we want to use to solve? Well, I'm looking for the push force, so I'm going to use this one. Notice I just created both equations anyways, just because it's habit. I just always create both of them before I move on. And now we're going to solve for the push force, so maybe we'll only use the first one, but whatever. So weight, as we said, is equal to mass times gravitational field strength. So mg times tan theta equals push force. Plug in my values, and I get a total answer of 5.44 newtons. Now I want you to remember that number. Now I asked you to remember that previous number because we're going to solve the problem all over again. Yes, we are, so sorry, but I'm going to do it again because I want to show you another way to solve these types of problems. We did the last one algebraically. We're going to do it again, but this time we're going to use graph paper. I took many slides to solve it algebraically, and oftentimes it takes up quite a bit of room. In order to solve it on graph paper, though, you can actually solve it pretty quickly as long as you're a little careful, and it actually takes very little math. So you'll see what I mean. Let's start with the one thing we do know in this problem, and that is I know the mass, and I can calculate the force of gravity. When we solve problems with graph paper, what we're doing is we're really just drawing the force diagram, and we're drawing it to scale. So we want to draw each force to a length that actually means how much force it actually is, and at the right angles. So the only force I actually know how to calculate in this case to start with is the force of gravity. So weight is equal to mass times gravitational field strength. Plug and chug, and I get weight is equal to 23.5 newtons. Now I'm going to draw that force downwards, but I need a scale to do that. I've established a scale. I've chosen that 1 inch is equal to 4 newtons. Now we're going to imagine each one of these squares is about an inch, though I know it's not. So that's what we're going to imagine. All right, so we're going to draw that, but in order to draw that force downwards, I need to first know what does that equate to on this scale, right? So 23.5 newtons, divide that by 4, and I get that should be represented by an arrow that is 5.875 inches long. Okay, so let's draw that. This arrow goes 1, 2, 3, 4, 5, and most of another one squares long, right? So here we go. This arrow represents 23.5 newtons of force. Now, I need to draw my other two arrows. I know there's one diagonal, and I know there's one over. Well, what can I relate to this one? Well, I know the diagonal can relate to this. The force upwards should be the same as the amount of force downwards, but this one's at diagonal, so how could we draw that? Well, the only other information I actually know is the angle of the diagonal is at 13 degrees. So I'm going to start with that. I'll put my protractor here, and I will draw a line that represents a 13-degree line. I know for sure that the arrow for the force, diagonal force, will go somewhere along this line. The problem is I just don't know how long. Well, what I do know is that the net force vertically is 0. So however far down this goes, the other force should go up the exact same amount. So I'm just going to draw until it is just as high up on the grid as this is down low. So 1, 2, 3, 4, 5, almost 6 squares high, just like the other one. Now let's clean this up a bit, get rid of my protractor, and I'll say, okay, what am I looking for again? I'm looking for this amount of force down here, right? Well, how does that relate to this situation? Well, I know the net force horizontally is 0, and I know this guy is pulling to the right, so he should pull to the left the same amount that he pulls to the right. So maybe we can find out how much force he's pulling to the right. I could maybe calculate, now that I know this length, I could maybe calculate using the scale. I don't know the length off the top of my head, but I can measure it with a ruler. I could calculate how strong this force is, but it doesn't really sound very interesting. I think all I really need to know is this amount here, so I can find this amount. I don't even really care how long the tension force is. So I'm going to take my handy dandy ruler, and I'm just going to measure how far over this travels. It looks like it's about 1 inch and maybe a quarter, maybe another eighth if you keep on going all the way up. So maybe 1.375 inches is what I'm estimating at. Now notice this is all estimation. You're going to be a little off. So if it's 1.375 to the right, that means this force down here should pull or be as long as 1.375 inches to the left. Okay, so now I know the length of my push force. All I have left is to use my scale and figure out exactly how much force that is. So when you have an arrow that's 1.375 inches long and it's 4 newtons per inch, you get a total force of 5.5 newtons.